Welcome back. We have covered quite a lot of ground so far. We learned how to implement a machine learning model and then we also saw how to evaluate the same. Now, one of the key objectives of any machine learning model is that it should perform well on unseen data. It's well and good building a model that is highly accurate on the training set, but it's also important that the model performs well on completely new, or as you can say, previously unseen data. That's what that matters. So in this video, we'll address this issue that how can a model perform impressively well on training data but fails when applied on the test or unseen data. This performance difference on the train and the test data is primarily due to the two factors known as overfitting and underfitting. But before we dive deeper into these concepts, let us first get an intuition about what these terms actually mean. So for this, we'll take an example and we'll go back to our school days. Imagine a group of three students in a classroom. Let's name them A, B, and C. Now, of course, no classroom is complete without a teacher, and I personally like the math class, so I'm going to say that this is our maths teacher. So, our maths teacher teaches us various concepts and theorems and solves some exercises in the classroom. It was always fun to, solve these questions in the class. But one thing which I particularly did not like, and I would say most of the students don't like, is the test. Now let's keep this classwork and test aside for a while and talk about the students in the class. So here we have student A and his hobby is coloring and sketching. So during a maths class, his mind always wanders to his sketchbook and he has no particular interest in learning about the new theorems or exercises that the teacher is teaching in the class. As a result, he pays very less attention to what is being taught. I believe every class has one particular student who is not very attentive. And also, every classroom has that one hyperactive student, often known as Mr. Know It All. This student in our case is student B. So, his hobby is answering every question in the class and he wants to be the best in the class. In order to gain attention of the teacher, student B writes down and learns every question that the teacher is solving in the class. He tries to memorize these and have it on his fingertips. In a nutshell, student B focuses too much on memorizing the exercises and doesn't really pays any attention to the concepts behind it. And then we have another student, student C. She loves new and challenging concepts and she really wants to learn something new every day. So her hobby is learning new things, and while in a maths class, she tries to understand the concept, she pays attention in the class and tries to grasp the idea behind problem solving and methodology. Now we have these three students, all of them having different personalities and interests, and our teacher. So the teacher is using a set of 20 questions in the class, and that's what we call the classwork, right? Now we know the characteristics of these three students, and we know how they would respond when the teacher is teaching. Student A would pay no attention in the class. Student B is trying to memorize the questions and their answers, while student C is actually paying attention to the concept being taught in the class. So once the teacher has finished explaining the 20 questions, she gives a quiz to the students. This quiz is based on the 20 questions that the teacher has taught in the class. And here are the results of the quiz. We already know that student A has no interest in the class to begin with, therefore, he randomly guesses and scores 50% in the quiz. Student B, on the other hand, actually breezes through the test quickest. During the class, he actually memorized every question and answer and was easily able to score a 98%. Almost a perfect score, right? Now we have student C, who we know learned how to solve the problem. She took her time and patiently scored a 92%, a pretty good score, I would say. Now, the teacher understands that student B and student C are doing very good, but she is interested in checking whether the students actually learned the concepts that she wanted to explain. So she has prepared another test for the students based on the concepts that she taught in the class, but the questions here are significantly different from the exercises that were covered. So the students have not seen this question before. Now let's see how the students performed. Student A, being distracted in the classroom, again uses random guessing and scores a 47%. Student B was slightly surprised looking at this test. He was confident that he knows every answer to the question taught in the class, but then he never encountered these new questions and he couldn't really understand how to solve them. Since he memorized the answers of the classwork, he's facing difficulty with the tricky questions. Therefore, he ends up scoring 69%. Now, student C was a problem solver and she invested her time in understanding the concepts. She scored 89% in the test. Let's quickly summarize what we have covered. We saw that student A was not interested in learning in the first place, therefore uses random guessing and scores consistently low scores. We can refer this as underlearning or underfitting. Student B, on the other hand, initially proved to be very promising. He scored 98 in the class test. But then he memorized the answers, right? He was limited to the classroom examples. Therefore, his score drops significantly to 69%. We refer to this as memorizing or overfitting. It means performing too well on the questions that he has previously seen, but failing terribly at the new different questions. Now, student C followed the problem solving approach and learned how to solve the questions. As a result, her performance was decent and consistent both the times. This is the optimal performance that we should be expecting, or the best fit, often called as optimum learning. Now, in this video, we have given you an intuition about what underfitting, overfitting, and best fit are. Now, we'll understand these concepts with respect to machine learning model. So, to demonstrate this, we'll be building a KNN model in this notebook. And in this notebook, we'll be using the same Titanic dataset which we have used during all of our classification challenges. So, let's start. We'll start with importing the necessary libraries. We have pandas, numpy, and matplotlib here. Pandas and numpy are basically used for data exploration and data cleaning, while matplotlib will be used for plotting the lines in the graphs. Then we'll use the pandas.read underscore CSV function for importing the dataset. The dataset name is dataclean.csv. So this is a cleaned version of the Titanic dataset and it has no missing values or categorical variables. So let's have a look at the dataset. Here are the first few rows. We have survived as our target variable, which has classes 0 and 1, and the other variables like age, fair, p class 1, 2, 3. So if you remember, p class was a categorical variable having class 1, class 2, and class 3. This has already been encoded. And similarly, if we want to check the missing values, we'll see that no feature has any missing values in this data. So now that the data is clean, we'll move forward and segregate the dependent and independent variables. So we are defining two variables here, x and y. X will contain all the input features and y will have the target variable. Now the next step is to scale the data, and we are going to use the standard scaler. So the standard scaler will basically bring all the values between -1 and 1. We'll first create an instance of standard scaler and implement it on the independent variables, which was x, right? Now we'll divide the total data set into training and test using the train test split function. So here we'll give the input x and y. X was all the independent features and y was our target. And this function returns four data sets: train x, train y, test x, and test y. This is analogous to our classwork and test from the previous example. So the train data or the classwork is basically on which the student learns, or in our case, the model learns. And the test data is similar to the test quiz for testing the performance of the model. Now we'll start with importing the KNN classifier and evaluation metric F1 score to evaluate the model performance. We have already studied KNN algorithms, so I'll skip the details of the algorithm here. Let's implement KNN for different k values. So I'll start with having the k is equals to 1. We fit the model on the training data. Then we make predictions on the train data as well as on the test data and calculate the F1 score in both the cases, right? So now when I run this block, I'll get the training F1 score and the test F1 score. The training comes out to be 97% and the test score is approximately 70%. So you can see a huge gap between these two scores. Now let's try a different k value. So let's say I change this value to 3 and run the cell again. So here the training score is 82 and test is 70. It looks like test score has reduced, but the difference is still significant. Now, hand tuning the value of k and deciding the right value is a pretty tedious task. So, we'll just automate our approach. So, I have created a custom function here. This will take in a list of k values and return us two lists, the train F1 and the test F1 scores. So, what I do here is for all the values in the list k, which could be even a range, I'll fit the KNN model on the train data and then predict on the training and the test data and calculate the score for the train and test. In the end, I append the scores for train and test in this empty list that we created. So this function returns us train F1 and test F1. So now just run this cell and then we can define the range of k. So here I've taken from 1 to 150. You can set this value. You can, if you want, set it to 1 to 200, or if you want to just look at the first 20 values, set it from 1 to 20 and so on. For now, I'm going with 1 to 150. And then I'm calling the above defined function. So this will give me the train F1 and the test F1 scores, right? And this might take some time to run because it is calculating the F1 score for all the values in the K. So here we are converting the lists that we got from the function defined into a data frame so that we can have a good look at it. And now here are the train scores and test scores for all the K values from 1 to up to 150. Now, these are just too many rows to digest, right? So is there any better way to understand this data? Well, obviously we can create a plot. That will be more insightful, right? So let's do that. Here I'm plotting the curves. We are plotting test F1 against the value K and then train F1 against the value K. And we are setting the color red and green to differentiate. So here is the plot. This green line shows the train F1 score and the red line gives us the test F1 scores. Now if you notice, the test score is essentially the same as the elbow curve that we saw previously. And other than that, we can also relate this graph to the student example that we covered previously. So at some points, the model is scoring well on the train data, but not so much on the test data, which was essentially like this student. And then similarly, we have some points where the model is not good on both the cases. So let's say that this is our region A, and then here the performance is almost similar. We'll name it region B. And then there's the region C, which, the model is not performing well either on train or on test. So now I have a question for you. Can you tell me which student of these A, B, C belong to which region? I have also added this question as an MCQ in the next section. So think about it and then move to the next video. Thank you. You must have gone through the questions we put forward in the previous video. So just a quick review here. This region A represents the student B, right? Who was very promising at the class test but did not perform as well on the next test that was conducted by the teacher. So this region A represents student B. Now in the case, we would say that the model is overfitting on the training data. Similarly, the models not performing well in both the cases are said to be underfitting model. This region C here represents the scenario. And this is similar to our student A, right? Who did not score well in both the tests. To decide the optimum value of K, we look at the region B here, where both the train accuracy and the test accuracy is almost similar, which is the ideal case, like the student C in our example. But let us take a step back and ask a question. Are we truly evaluating our model on completely unseen data? Yes, no, confused? Well, pay attention here. While calculating the value of K, we are looking at the F1 score for both train and the test data. So in a way, we are actually using the test data, right? I can say that this test data is not completely new for the model. The model has already seen this data. So it is actually dependent on this data. Let us see that in practice. So if I give the model a different set, let's say changing the random state value to 42 here. In this case, the distribution of the rows in train and test would be different. Now if we implement this and we plot the graph, this graph is very different from the previous graph. Here the optimum value of K was about 20, right? And in this case, if you observe, it will be close to 25. So we can see that the optimum value of k changed. Now let's say I do it for some other random state. Let me put it 0. And again, if I run the 3 cells, this plot is obviously different from the previous plot that we saw. So what I'm trying to say here is, my model is actually dependent on the test data. It may or may not perform this well on some completely new data that we give the model. So is there another way to decide the value of k without having to use the test data? Well, actually there is. In order to do that, we'll introduce a validation set in addition to the test set. Now that we understand what underfitting, overfitting, and best fit models mean, my question here is, will the best fit model work well on completely unseen data? You might be tempted to answer yes, but hold on. Let's first truly understand what unseen data is. So far, we have been using the test set as unseen data, but was it really unseen? In the notebook we saw earlier, we selected the optimum value of k based on its performance on the training and the test data. So the model actually has a look at the test data. It is not truly unseen. We are looking at the model performance on the test data to decide the optimum value of k. This means we are not testing the performance on completely new data. So our model might fail in that case. And it might be possible that the model is not very generalized and does not perform well on a completely new or unseen data, which might be disastrous in the real world scenario. So, how do we actually generate this unseen data? We need a dataset to build and implement any machine learning model. We divide this dataset into two parts called the training set and the test set. So far, we have been optimizing the model based on the test set, but we need to have some data which is completely unknown to the model. So, what do we do now? We do not use the test set to optimize the model, but another partition called the validation set. So, from the remaining training data that we have, we introduced a new data set called the validation set. We use this validation set for the optimization of the model, and we keep the test set for final evaluation only. In the upcoming videos, we'll be looking at techniques shown on this slide through which we can perform the optimization of our model. These are basically the techniques used to create the validation set. The validation set is a critical aspect of working with machine learning models. And in this video, we'll be looking at one of the common validation techniques, the holdout validation. Now, here, if you see, we have divided the dataset randomly into three parts. The first is training, the second is validation, and the third is testing. The distribution shown here is 60-20-20, but there's no hard and fast rule. The distribution could be 70-15-15 or 70-20-10 and so on. Now here we'll use the validation set to tune the model, or say selecting the right value of k, and the test value as a completely unseen data for the model. So to understand holdout validation, let's recall the Titanic dataset. Here we have to predict the dependent variable whether a person survived or not. From this data, we'll need to generate a validation and a test data. First of all, we'll shuffle the whole data set. So here you can see the shuffled data, and then simply take out a subset which will be our test data. And this part will not be used in any way to train the model. From the remaining data, we'll take out another subset of data which is called the validation set, while the other portion is the training set. Simple, right? The validation set we just created looks okay. But think for a moment, can anything go wrong with this? The straightforward holdout validation set we just created is prone to certain issues. The validation set and the train set could potentially have different distributions. How? Let me explain. Consider this example. The blue bar represents the class 0 and the red bar represents the class 1. Now it is completely possible that the train data may have a very few percentage of class 1 while a validation set has a higher percentage, or in an extreme case, the train data has all the rows with class 1 while validation has nothing. So in such a scenario, even a very good predictive model might not perform well on the validation dataset. So how do we solve this issue? By creating a stratified holdout validation set. Now the stratified holdout set divides the data in such a manner that the train set and the validation set have the same distribution of target class. So we can clearly see in this example, the train and the validation have equal distribution of classes 1 and 0. But there's a catch. The holdout validation requires a good chunk of data to be kept aside. This can be an issue when the data is small or when we want to capture a complex relation, which requires more data to train on. In this notebook, we'll learn how to divide the dataset into the train set, the holdout validation set, and the test set. We'll also observe the effect of using the stratified split. So let's begin. You must be familiar with these initial steps by now. Here we are starting with importing the libraries NumPy, Pandas, and Matplotlib. NumPy and Pandas mainly used for data cleaning and exploration, and Matplotlib to plot the curves. Now the next step is to import the data. So we have data cleaned. This is again the Titanic dataset that we saw previously and the clean version of it. So looking at the first few rows of this data, I have survived as my target variable and the rest of the features. And just to confirm that there are no missing values, I'll use the .isNull function. So the next step is separating the data into dependent and independent variables. For this, I'm using two variables, data x and data y. Data x stores all the independent features and data y has the target variable. Now we'll learn how to create the validation and the test set. So I'm using the train test split function again. And to the train test split, I'm giving the input data x and data y, which is basically my complete data, and then setting this test size to 0.2. So I'm storing 20% of the complete data for testing, setting a random state and the stratified none. Now this will give me four results. Test x and test y will be the testing data, and train 1x and train 1y will be my train data. Now, in order to create the validation set, I'll be using this train 1x and train 1y, which is basically this part, and then creating a validation set out of this. So now this becomes a two-step process. Firstly, I created the test data from the complete data. Now I'm creating a validation data from the remaining training data. So here again, I'll use the train test split. And as input now, I'll give the train 1x and the train 1y, which is this part. The test size is set to 0.2, which means 20% of this data will be stored for validation, a random state, and the stratified none. So when I run these cells, I'll get my train and validation and test data. Now here we have 569 rows in training data, 143 for validation, and 179 for test. Remember, we have currently set the stratify as none. So let's look at the distribution of the target class in train, test, and validation. Here we use the value counts function along with the length of the train data. So let's say if I simply use the value counts, I'll get the count of rows with class 0 and class 1. So 364 for 0 and 205 for 1. But this is not exactly very intuitive, so I'm trying to use the percentage. So here I'll use the length of the train y, and this will return me the percentage. So I have 63% rows having class 0 and 36% having class 1. Similarly, when I find out for the validation y and test, I'll get the distribution something like this. Now, as you can see, the distribution of classes in the train, test, and validation is not equal. So what do you think we should do? Exactly, we'll set the stratify. So instead of using none, I'll use the target variable. In this case, my data y is the target. So I'll set this as data y and run this cell. And similarly, while creating the validation set, train 1y is my target, right? So I'll set that. And now when we check the distribution for the train, validation, and test, the distribution of classes 0 and 1 in all the three cases is equal. So in this notebook, we saw the implementation of holdout validation and stratified holdout validation. We know what is holdout validation and stratified holdout validation techniques. Both have their uses, but we encountered an issue, remember? We had to keep aside a subset of data for validation, which we could not use during the training time. Now in this video, we'll be looking at k-fold cross-validation method, which will address this issue. Previously, while making a holdout validation set, we made three partitions of the dataset as shown here for training, validation, and testing. In case of cross-validation, we do not need to explicitly make the validation set. As this video progresses, you'll understand why. But before we look at why cross-validation is useful, let us understand how can we apply it. So first of all, we shuffle the whole dataset or randomize the order of the rows in the dataset. Then we split the data into k equal groups or k equal folds as we say, as shown here. Now for every unique group, we do the following. We take a group as a holdout set as shown in the red box and take the remaining data as training set as in the black box here. Now we train the model on this part and evaluate on this holdout set, and the evaluation results of this model are stored. Finally, we repeat this second step with all the other groups. So basically what we are doing here is dividing up the dataset into groups, and we are using one group at a time as validation set and the rest for training. In the next iteration, the validation set changes. So how does k-fold cross-validation solves the issue that we encountered? In case of holdout validation technique, we keep a part of the data aside while that is not required in the k-fold cross-validation. Also, as we use a single validation set, there are chances that the model might overfit on this validation data. But in k-fold cross-validation, we have multiple validation sets. So the chances of model overfitting on the validation set reduces. Now, in case of k-fold cross-validation, we can also ensure the consistency of the model since the model is evaluated on multiple validation sets and not one. Now, how do we decide the value of the number of folds or k? I'm sure you've been thinking this since the start of the video. So let's take a moment to understand how to decide the value of k. Generally, having a validation set containing 10 to 20% of the data is considered good. Therefore, a good value of k should lie between 5 to 10. Also, a good value of k should be selected such that it takes as much data as possible for training, but the validation set should be enough to give statistically significant results. Another point to note is that if we set the value of k very low, say k is equals to 1, in that case the training set will be same as the validation set. And if we set it like k is equals to 2, it will be a 50-50 split. Therefore, the data for training will be relatively low. When we go beyond the value of 10, there will be more and more data for training, and the size of validation set will keep on decreasing. The computational complexity in this case also increases. When we assign an extreme value to k, which would be equal to the number of observations, in that case, the number of models built over the dataset will be equal to the number of observations in the dataset. This is called the leave one out cross validation. It is an extreme case of k-fold cross validation. Let's take a closer look at it. Leave one out cross validation, as we saw, means using a very large number of models over almost the complete dataset. Therefore, it's computationally very expensive. And as you might have guessed, this technique is not significant when the size of data is very large. Now let me explain this using a simple example. So suppose we have two datasets as shown here. One on the left has only 10 instances and the one on the right has 10,000 instances. Now say we select the value of k as 5. In this case, the validation set for the right hand side would be 2 instances. On the left, it would be 2000 instances. If we look closely, the training data on left side is very low for a predictive model, and any small increase in the amount of data would be beneficial to train the model. So say we consider the value of k as 10, the training size here increases from 8 to 9, while in this case the increase would be say 1000 points, which is not very significant. So to summarize, we can say that leave one out cross validation is very useful practice when working with small datasets, especially for datasets below 100 instances. In order to find a middle group between the computational expense and the datasets, which are not very small, we can use the concept of leave p out cross validation and select a value of p according to the computational complexity and the training data required. So now we know how to validate the performance of our model using k-fold cross validation. This is one of the most commonly used validation techniques out there, especially in data science competitions. We'll start with importing the essential libraries, pandas, numpy, and matplotlib. Then we'll read the dataset. This is again the cleaned version of the Titanic dataset that we have been using. Here's a look at the first few rows of the dataset. We can see no categorical variables and there are no missing values. Now we'll separate the dataset into independent and dependent variables represented by x and y respectively. Now before applying the KNN model, we'll scale the values. So we'll apply the standard scaler on x, which is all our independent features. Then we'll create a train and test set using the train test split. We are giving the input as x and y, which is our complete data, a random state, and stratify set to y. So let's run this cell. Now we'll import a KNN class, which we'll be using in this notebook. Now remember in the last video we understood that k-fold cross-validation technique can be used to check the consistency of the model. So in order to check that, we'll be using the cross-validation score function and we'll first import this. Then in this function we'll pass the following values. We have KNN class with n neighbors set to 1 and then our train x and train y and the number of folds here is set to 10. So this cross-val score will return an array of 10 values which will consist the validation score for each of the folds. So let's see that. Here are the 10 values. Now the list by itself is not of much use. So we'll take the mean of these scores. Now if you think about it, higher mean would imply a better model. Why? Because we want that the model should perform well or get a higher score in each of these validation sets, right? So if each of these score is high, the overall mean would be high. Also for checking the consistency of the model score should not vary much. So it should not be like for the first validation set it has 0.4 and for another validation set it has 0.98. So to check that, we can calculate the standard deviation of these scores. So in the next cell we are calculating the mean and the standard deviation. And the mean here comes out to be 73 while the standard deviation is 7.2. Now remember we have these values for the n neighbors is equals to 1. Let's try changing that. I'll make it 3 and now when I run these cells again, I see that the mean has improved to 77.2 and standard deviation dropped to 5.2. So n neighbors 3 is a better idea. Now manually checking the values could be a long process, so instead we'll automate this. And here's the function for the same. We are taking a list of n neighbors and for each value in this list, we are calculating the score using the cross-val score function and then the mean and standard deviation for this score. This mean and standard deviation obtained are then stored in a list, in an empty list that we have defined here. And this function will return this mean and standard deviation value. So let's run this cell. And now we can check for any values of n neighbors. So I'm here taking from 1 to 50 and calculating the mean and standard deviation. Now that we have the mean and standard deviation for 50 values, we'll plot these. So here's the plot. This is a plot for the mean values across all the n neighbors. So we can see the value from 0 to 50. And if you look closely, the mean score corresponding to low values of n neighbors is fairly low. That means the model is trained poorly and hasn't generalized over the validation sets. And if you see, the highest value of mean would be somewhere between 10 and 20 value of n neighbors. So we'll plot this mean curve again and this time using only the n neighbors value from 10 to 20. So here is the plot. And now we can clearly see that the maximum value is at 14 and probably the second best is 12, right? But now the question is this model stable and consistent for all the validation sets? So to check that, let's look at the standard deviation for this model for n neighbors again between 10 to 20. Now here if we plot this, you will see that actually the standard deviation is quite low for the n neighbors 14 and so is for the value 12. Which means that at this value of n neighbors, the model has generalized pretty well. Also remember we created a test set initially. Note that we have not used the test set to find out the optimum value of k. That test set can be treated as a completely unseen data. Now let's look at the performance on the test set. So I'm going to here set the value of n neighbors to be 14. And if I check the performance, that's a really good score. So I see 81 on the train set and again 81 on the test. So it's 81.6 and 81.1 here. So we saw how cross validation is implemented and it helped us in selecting the optimum value of k neighbors. Moreover, the model we selected was not lucky and was consistent with results, even generalized on the unseen data very well. Now, in this video, we'll see how overfitting and underfitting actually occurs in machine learning. So, we are already familiar with the KNN algorithm and we have seen this graph previously, right? It shows the model score for different k values. A higher score here implies a better model. Now, let's look at the graph closely. In this graph, this region right here is where both validation score and the train score are low. If we recall from the classroom example, which student do you think this graph would represent? Student A, right? His hobby was coloring and he was not really interested in learning about maths to begin with. So, in other words, we can say that the student A was not interested in learning math at all and used random guessing in the test. Similarly, this region in the graph represents a model that is not learning well due to some simpler assumptions that the model might have. Let's look at an example. Here is the model that has to classify the blue points and the red points, and as you can see, the model isn't performing well because it has an assumption that a simple straight line would be able to do the job. This is an example where the model exhibits high bias. High bias means that the model is not able to learn available signals or patterns in the data. Now let's look at this region here in the graph. It is clear that the validation score is pretty low, but the training score is significantly high. So if we again recall from the classroom example, which student do you think this graph would represent? It would be student B. Student B had a very good score on the classroom quiz, but performance dropped significantly in the test quiz. This was because he tried to memorize each and every example over understanding the concepts behind the topic. And so, during the test quiz, he was not able to perform well. Similarly, in predictive modeling, this is an example where the model is overfitting on the training set. Here, the model is trying to classify each and every point in the training data. So, as you can see, this model is very complex. Now, if say these 2 points were not in the data set, in that case, the line would have been something like this, right? If this blue point and this blue point weren't here. Similarly, if say I add another point here, if there was another red point at this place, then the model would go something like this. So what I'm trying to say is, if I remove these 2 points, the decision line or surface may take a simpler shape, and if I add 1 point here, it will again change the shape of the decision line or the surface. So you see the problem? Here our model is very sensitive to the training points, or as I can say that it is learning noise along with the signals or the patterns it should. Our focus should be only on learning the patterns and not this noise. And due to the same reason, the decision surface or the decision line will vary a lot with any change in the training data. That leads to high variance or overfitting. Now let's look at this region. This is where the train score and the validation score are almost consistent and very similar. We can also see that this score is really good, so it's more than 0.7. Now if you recall, we had students C from our example who performed significantly well in both the classroom test and the quiz. This is because the student C was interested in learning the concepts rather than memorizing like the student B. So in predictive modeling, this is best fitting model and this is the ideal case. So it may look like this is misclassifying some points here and here, but then these points can be considered as noise and not the signals in the data. Therefore, not capturing those extreme cases is a wise choice. Now, once we have learned about the bias and the variance, let us summarize how it looks in predictive modeling. In high bias models, the model assumptions are very simple. We are not able to capture the available signal of the data because of these simple assumptions. For KNN, this happens at a very high K value, and the resultant model looks something like this here. In case of high variance model, the model is just too complex and captures the noise along with the signals. Therefore, the decision boundary gets very sensitive to the training points and trying to capture every single instance in the dataset. This is clearly visible for the very low K values here. Now, the last one is the ideal case in which we are somewhere in between the high bias and the high variance model. It generalizes the dataset ideally and captures signal optimally while avoiding the noise. So let's now talk collectively about the concepts we learned so far: the bias, variance, overfitting, underfitting, and the model complexity with respect to KNN. To simplify the understanding, and we'll go through this table column by column. So let's first talk about the student A. Student A is associated with very high bias and underfitting. Also, this model corresponding to high bias is very simple. Remember that very simple line that we drew? Now, in that case, the model complexity was very low, which meant that the model was not able to generalize well and hence was underfitting. And this was observed at a k ranging from greater than, say, 20. So, for very high values of k, we observed high bias and underfitting. Now, if you observe that as k decreases, the model score increases. But then we move to a region where the model complexity is very, very high, which takes us to student B. This region represents student B, or in the model case, we say a region where the model has very high variance. This model is clearly overfitting, and the range of k values, as you can observe from the graph, is something k less than 10. Now, for this very high complex model, we were again not able to get very good results on the test set, right? So, we found a best fit model which represents our student C from the example. This model was optimally between the high bias and the high variance models, and the k range value would be around 12 to 20, as you can see. The model was not very complex but also not very simple. So now if you observe with respect to this best fit model, on the left of this best fit model is the overfitting region, where we have a very good score on the train set but a very low score on the test set, and this was a region where the model was very complex. On the right of this region was a model which was very simple, giving a bad score on both of them. So we specified this as a high bias region and this as a high variance region. So I think it's safe to ask now that is there any relationship between bias and variance? Let's find out. Let's first talk about the bias error. So you are already familiar with this graph now, and this was our high bias region. According to these two, the high bias is observed when the model is very simple and it's observed at very high values of k. Something like this line was our very simple model and it comes from values very high k. So model complexity here was very low. So for a very low model complexity, you get a high bias. Now plotting this in the form of a curve, I would say that if x-axis has the complexity, so for a very low complexity, something like this, you have a very high bias. Now as the value of k decreases, the model complexity obviously increases. Remember that curve that we saw for overfitting model? This was a very complex model and which we saw between 0 to 10. So for very small values of k, we had a very complex model, but the bias there was very low. Now if we perform the same analysis for variance, we would see that for a very low value of k, we got a very high complexity, which is this region, and here we observed a very high variance. And as the complexity decreases, we move towards this region, which has low variance but high bias. So now if we try to combine these bias and variance curves, let's just plot them together. And this combined graph, we can clearly see that represents a very good relationship between bias and variance. So when the variance is high with respect to model complexity, the bias is low. And on the contrary, when the variance is low, we see that the bias is very high. So we'll now introduce you to one more curve, which is the generalization error. Now in broad sense, it is basically the sum of the variance error and the bias error. So this curve will be useful to define our optimum model, which should be somewhere between the high bias and the high variance region. So we'll try to plot this region where the generalization error is very low, which clearly comes out to be at a complexity where both variance and bias errors are low. So to left of this very complex model, we see that we have a very high bias region, and to the right of this optimum model, we have a very high variance region. So we have understood the relationship between the bias and the variance using the bias variance trade-off graph. Thank you.